Okay, so we're going to continue our discussion of GIS and spatial epidemiology here, GIS basics. So GIS is a layer-based methodology. That is, it takes the real world and slices it up into thematic slices, each representing a different aspect of that world. And part of the strength of GIS is that we can take data from one layer, for example, and associate it with another. So if you look at this picture, and you think of a layer above all these, for example, that has places of disease incidence or households where the cases appear, then we can associate all that data from streets, political boundaries, land usage, elevation, and all of these things can be associated with those particular locations, creating sort of an extra set of data sets that we can use to study associations between exposures and disease. So GIS data is spatial in nature. Here's an example of the world cut up into latitude and longitude coordinates. So longitude is along the x-axis, latitude is along the y-axis. 0, 0 is at Greenwich. Longitude 0 is in Greenwich, England, just like our time system is located in Greenwich, England. And then everything to the east of Greenwich, England is positive longitude. Everything to the west is negative longitude. Everything in the northern hemisphere is positive latitude, and everything in the southern hemisphere is negative latitude. So you can sort of tell at least what quadrant things are in based on the coordinates themselves. So I'm not going to ask you to do anything with longitude, latitude coordinates, but I just want to sort of get you to understand what these things are. Longitude is on the x-axis, latitude is on the y-axis. So in GIS, there are two different types of data models. The first is what we call vector data, which is sort of lines and points and polygons, and we're going to see an example of that in a second. And the second is raster data, which is where the world is kind of set up like a picture is, and there's dots, and each dot has a different value or a different color that represents sort of a different thing about the world. We're going to talk about that in a second. So here, there's two different ways of approaching the world. We have the real world, and there's vector data, and there's raster data. We can represent the real world using either. Some aspects of the world are better represented with vector data. Some aspects of the world are better represented with raster data. So for example, we have vector layers in GIS. Vector layers comprise points, lines, and polygons, and I think you can think about what different examples of might be suited to each of these. So points, for example, might be suited to household locations or locations of disease incidence. Lines might be something like roadways or riverways that might contribute to disease incidence. So for example, like malaria incidents might be associated with rivers, and your GIS layer of rivers is line-based river, and you can calculate the distance. Polygons are just like points and lines, in that they have points that put them together, but they have area, like you learned in math class. And polygons can be things like administrative areas, zones, or whatever. Yeah, so points, lines, and polygons, these are vector layers. And I'm not expecting you to know any of this stuff. It's just, to get you familiar with the sort of basic terminology, because they'll come up in some of the readings. So the difference here, points, lines, and polygons. Points are locations on the map that only have a single x and y coordinate for each feature. So, points, locations of households. Lines are locations that consist of two x and y coordinates, like put together by a line. Polygons are areas that can be defined by space between 3 or more XY coordinates, and then there's an area inside. Raster layers look like this. So this is like, this is elevation, I believe, and the light colors represent low elevation, and the dark colors represent high elevation. So maybe? No, it's the opposite. Light colors represent high elevation, and dark colors represent low elevation. And the way this is mapped out is there's a grid, right? And you have, columns, X and Y, like you would have a plane in mathematics, and each pixel or cell within that grid has a different value representing elevation. So, and the way they've done this here is they've represented these different values using different colors. So this picture sort of pops out. So what makes data spatial? Having coordinates, place name, postal codes, distance and bearing, descriptions. Like I said, spatial data can be explicit in having latitude and longitude, or it can be implicit in just having a place name that identifies it as being a certain area. The point is, spatial data has to have some information on space. Primary functions in GIS, doing things like capturing data, so capturing things to put into your different data models, be they vector or raster. Storing data, storing geographic data in vector and raster formats, querying data, pulling out different aspects of your data set, analyzing them, answering questions, displaying them, making nice pretty pictures, and outputting them into a variety of formats. So GIS is not a software, it is a methodology. And it's a very expansive methodology that people use. So I think people sort of get caught up, in thinking, that it's like an Excel or software package, and it's not. It's science. That's why I think geographic information science is actually a better way to explain it. GIS data structures, multiple layers of spatial data are integrated within GIS. Remember, GIS is a layer-based methodology, taking the real world and slicing it up into thematic layers. And this allows for different queries and functions to be performed across different layers, and visualization of multiple spatial data sets at once. So there's a lot of information we can draw from here. And for us as epidemiologists, this is our bread and butter. We have outcomes, and we find risk factors for disease. We want to find locations of outcomes so that we can inform public health professionals of where they need to target resources. This is really what we're about. Databases look like this. GIS for analysis, there's a huge range of image processing and data analysis tools available. Geocoding, buffer analysis, spatial autocorrelation, travel time, density estimations. I'm not going to go over them all here in this class because that's not what this class is about, but I sort of encourage you to explore GIS as a possibility for what you might do in the future. Spatial statistics and spatial epidemiology is a massive field, and spatial applications exist in all different types of disciplines, including ecology, not just public health, business, economics, political science, all different kinds of things. Public health terms for applications, we're usually looking at general disease mapping and spatial analysis, trying to figure out where incidence is. Environmental health, associating disease outcomes with point source exposures. Healthcare resource planning and policy, figuring out where to target public health efforts. And disaster planning and response. So what places are at risk, preparing for the worst. So when we talk about data integration, roads, land parcels, population, utilities, landmines, yeah. Hospitals, primary healthcare facilities, clinics, refugee camps, wells, sanitation. There's so many applications out there that you can apply it to. Visual data, does it matter? I would say yes, 100% it does. So when we look at cancer mortality rates by county in this picture, I think that it's not hard to figure out why a map like this would be important. This is age-adjusted 1970 U.S. population for different sorts of lung and trachea cancers. This should definitely tell you something, and I want you to think about what it tells you. I know what it tells me, for sure. Southern United States, mountain states. Very red there. I would say that's a real problem, and I sort of leave it to you to think about why that might be. Poverty indicators, So poverty is complex. It's not just simply not having money. There's all different other aspects to poverty. Lack of access to quality education, lack of access to health care, lack of access to economic opportunities. All these things contribute to poverty. And so what people do is take all those informations and create poverty maps, or poverty indicators like we see here. And this gets even more complicated when you go to developing countries where economic information such as taxation or income is unavailable. Important caveat. Back again. Correlation does, so caveat here, maps can lie. It's very true. You know, tech effect. People see it on the internet and they think it's true, and we all know that's not true. And the ecological fallacy, looking at large combined groups of case patients, is not the same as looking at individuals, for sure. But I think what you really have to take home here is correlation does not imply causation. And just because we find an association or even a spatial association doesn't necessarily mean those two things are truly linked together. They can have, for example, the same cause, the same root cause, or just be sort of coincidentally linked. So you have to be a little bit careful with spatial epidemiology. It's very easy to come up with maps and pictures and sort of assume associations, but you have to have some sort of explanation or some sort of evidence to why that association would exist. So, definitely be careful. Visualizations for disease mapping. There are many ways to display disease data. Map individual cases like points, for example. You can map total per reporting area, so districts, aggregates by district. Standardized incidence or prevalence ratios, looking at incidence per 100,000 people in different counties or even among different groups. Age standardized rates, correlations with environmental parameters. There's all different sort of options that you can use for disease mapping. Okay, so I think that's it. Those final slides I'm not really going to talk about, but I really want to come back to this. So correlation does not imply causation. As a spatial epidemiologist myself, I can tell you how easy it is to come up with different sort of associations and nice maps and create convincing arguments, but they might, you have to be somewhat skeptical for sure. And also how you present data is important. You should present data in a way that's sort of scientifically neutral but still gets the message across. There's all different ways of coloring things in, to create sort of a little bit misleading messages sometimes. Yeah, so anyway, if you have any questions, hit me up. I'm here to help you. See y'all.